Hello there, hope you're keeping well. Welcome to the wonderful world of radio frequency and electronics engineering. On the bench for repair today is a good old ICOM756 PRO3. This one's quite poorly by all accounts. It's been brought to me by a local radio amateur for repair because it's getting excessively hot while it's in standby mode, even without being turned on. And first noticed this when the transceiver was just listening to radio station, not even transmitting, and the power supply that he uses to power the unit, which is rated at about 60 amps, the fan kept cutting in and out for the cooling of the power supply, which he thought was quite strange because it's not meant to draw that kind of current on receive mode, obviously. So I wondered if I had a problem with his power supply. Checked that out and it's apparently been okay. So he's obviously looked at the radio, and because of the way that it's been fixed in the bench, because he has it like enclosed with a wooden panel round it, he's removed a transceiver to have a look at the rear of the radio, and the rear of the radio down there is where the power amplifier is for the transmitter, was very, very hot when you touch that area of the rear of the transceiver, because that's where there's a fan and it blows all the hot air out that way. So yeah, so I brought it round for a look. I've got one of these radios myself and it's been a lovely radio. I've always enjoyed using these. Very nice radio indeed. They've been around for some time now, but they're great transceivers, I must admit. My ICOM756 is a PRO3 as well, and there were different models in the 756 range, this being the last of them I believe, which was a PRO3 like mine. These obviously have band scope on them, dual VFO, so you can see or listen to two frequencies at the same time. Basically 30 kHz to 60 MHz continuous coverage, and 100 watts RF output power on transmit, and indeed very good filtering and lovely radio. Very, very nice radio, nice and compact. So yeah, very, very nice sort of bass radio, and you can use it mobile as well, obviously, because it works from 12 volts 13.8 volts, so you can actually take it out in the car if you wanted to do that and work mobile or DX that way. So really nice radio, very sort of hybrid type that in the early days before SDR came out to any big advantage, these were sort of leading the way in terms of that. Not really a troublesome radio as a 756, to be honest. It's always been quite reliable set. You do get little problems with the display, backlight packing in and usual things like that, but more often than not they are actually quite reliable. There have been some issues with the antenna changeover relays and the ATU relays getting a bit tarnished and sticking and little problems like that, but nothing major. So yeah, quite concerning is this when you turn the power on and then it draws all this current. So let's have a look at that. We've got a power supply here which was set up. Now this radio transceiver, it's very important to note when it's on transmit at 100 watts it draws about 25 amps, which is part of the spec of this radio, and this power supply can only produce 15 amps. So initially I'm just going to use this power supply just to verify the fault that is the standby current before the power supply, before the radio switched on, and then we can always switch over then to another power supply I have here, which has analog meters on it, and that can deliver up to about 40 amps, so we might need that, but I think this will be adequate just for now. So what I'll do is I'll just connect the positive supply up, and we've done that just there. Just back that pot off, that post off. So we're getting 4 amps drawn even without any power up at all at the moment. So yeah, that's strange, isn't it? Because there's no power at all on this radio and we're drawing 4 amps. So that's interesting. Now there is a filter unit down there at the back for the power supply. The power supply runs through that and then goes into the radio. So if I just unplug the power lead at the back, which I have there, then that confirms it's not the DC filter unit which this cable connects to. It's definitely the radio, because as we've seen, the current has gone. So that rules that out. Plugged it back in now into the back of the transceiver, and we're getting 4 amps drawn again. Okay, I'll turn the transceiver on. We've got the antenna on the back of this radio connected into the radio test set there as well, which is in TX test. Now it's drawing more current, 6-7 amps. So really you could say that's 2 or 3 amps on top of the 4-5 amps that it was drawing earlier while it was powered off. So it's like adding to the current to make it 7.5 amps. I'll just have a feel at the back. It is warmish at the back, but not just lukewarm at the moment at the back there. So we've got an RF power potentiometer there, which is set at minimum at the moment. At that point it should have 5 watts. And then just select FM mode. We're on 24.9795 on FM mode. Let's just see. Yeah, it's only doing 291 milliwatts on that frequency. Now I'll put the spectrum analyzer on the radio test set, because if it was self-oscillating, because again we're in receive mode, it's drawing 7 amps. If the power amplifier was self-oscillating in the rear, and obviously it was producing RF output, we will be able to detect that even if the transmit receive switch relay was in the receive position. Obviously it's a bit defeatist because we have to press the transmit button in order to connect it up, but I'm not seeing the signs of self-oscillation that you would normally find there. Normally with the antenna tuner off and the different bands that we selected, 2 megahertz, we would see massive swings normally in the depending what part self-oscillating, of course. If it's the RFPA, it could be oscillating at any old frequency, but basically to me that looks like as if it's not the RFPA that's self-oscillating, because we'd see some form of RF breakthrough on the spectrum analyzer, and we'd definitely see something coming through, and it would be with the tuner being out of circuit. We would see differences if the PLLs were in self-oscillation or the drive circuits to the RF amp, and we would see that. So obviously we're not seeing that. Now if I transmit again and I go to the different frequency bands, I'm not getting any change in current. You see, it's 7.78 amps no matter which band I'm on. Now if it was self-oscillating, we would get a different current consumption on different frequency bands, because the antenna tuner's not in, and obviously it would affect the impedance of the amplifier when we're transmitting into the RF load. So any self-oscillations will be dampened, and that's not happening here. So we're getting the same current drawn no matter where we are on the frequency bands. So if I switch the power off again, and now we're dropping down to 3.8 amps. So yeah, that does seem a bit excessive. We're getting like nearly another 3-4 amps draw there on top of that when we switch the unit on at 7 amps or there around. So it does seem a little bit strange. The RF power as well, when it's set at minimum there, that potentiometer on that frequency, we should be getting 5 watts RF power, but we're not. We're only getting 228 milliwatts. So that does seem a little strange. Now the power supply that I've got on at the moment is struggling. Even though it's rated to 15 amps, it is actually struggling to deliver that current without affecting the voltage. So we're going to switch over now to the high current analog metered power supply that can deliver around about 30 amps, and that will then give us a true reading then and stability for this transceiver, so we can test the RF power properly into the radio test set. Okay, so we'll just have a quick gander at the specification. Now when we look at the spec down here, regarding this data here, current drain. So it says maximum power, which is 100 watts RF power. It'll draw 23 amps maximum. Receive standby current should be 3 amp typical, but obviously with the volume wound up 3.5 amps, so just under that, 3.3 amps. So we're not expecting the 7+ amps that we're getting there. That's excessive, is that? We've obviously got some diagrams here as well at the RF section at the back, and this is the area he said was getting quite hot, and yeah, so it looks as if apparently this area here is getting very, very hot. It's cooler on this side, he said, so it's obviously something associated in this sort of locality with the RF power amplifier. We've got the driver transistors and pre-driver for the RF power amplifier mounted here, which are in TO220 packaged transistors, and then with the two big RF power amplifier devices there. So if we just zoom in, we can see a little bit more detail even before we've whipped the lid off. It's good that the service manual has the pictures of the board. So we've got the two main PA transistors there, obviously the input transformer and the output transformer. We've got a relay here, presumably for switching DC volts, I would say. May not be, might be an RF switch relay as well, but we'll look at that. We've got a fuse here. We've obviously got DC supply, as you can see on the red wire, coming directly into the PA, positive and negative there on these two terminals. So that comes straight in from the power supply, and then we've also obviously got a RF coaxial cable there as well. So input and output, looks like that's the input coaxial cable, and this is the output coaxial cable from the amplifier that then goes onto the ATU board, antenna tuning unit. So it could be that yeah, we had a very similar problem, although I'm jumping ahead here until we know, but we had issues with these types of transistors before on the Kenwood TS2000, if you remember that. And it's funny because I think this uses, this diagram uses the same kind of devices that was on the Kenwood TS2000, and I'm just looking now. There we are, look. So the drive circuit is 2SC1972s, which is the same problem that we had on the Kenwood TS2000, the 2SC1972s. One of them was stuffed, if I remember rightly, and it was drawing current just like this when it was on, you know, switched off basically. So yeah, because these are obviously across the permanent supply rail, so it may be a very similar problem, fingers crossed. Or it could just be a biasing adjustment. It could be that the bias, these potentiometers that set the bias up for both the driver and pre-driver and then the PA maybe are out of adjustment. Could be something like that. Who knows, but we'll delve into it a bit further now we've got a bit of information a bit further. So here on the bench we've got the power supply. Now I'm just going to connect up this terminal here now for the thing. As already we can see we've got a current draw even without it being turned on. So again, that leads me to believe that there's something PA related. There's no smells on the radio. I've had a right good sniff around it to see if there's any burning smell or anything like that, and there isn't, so that's a good sign. There's no smoke or flames coming out the back, although we'll not keep it on for too long. I'm just feeling behind. It is a little warm behind. Now on 50.622 megahertz that we're on there, if I turn the RF power down there and then select the FM mode, that's FM. Now in theory at low power it should be doing 5 watts on the radio test set, and we'll be interested to see whether we get that. Now the RF power is obviously indicated in the top right hand corner there. It says power, and as you can see there we're only in if my eyes don't deceive me, milliwatts. Now, as I begin to turn the RF power amplifier up, I can see the current going right up now to around about 15 amps there. At that point there, we're drawing 15 amps. And now we're doing 20 something watts. And then that's nearly 20 amps at full power. And it's only doing 40 watts. So it should be doing 100 watts there. So if I just zoom back out again, and then we have a look at the power supply. So if I key up, you can see on the power supply there, if I turn the RF power down to the far left, that potentiometer should be doing 5 watts. It's drawing about 11 amps on transmit, and we're only getting 390 milliwatts out of it. That's halfway. It should be doing 50 watts there, and it's only doing 9.37 watts, and we're already drawing 15 amps on transmit there. And then if I turn it fully clockwise, so we're doing maximum power, it's only doing 49 watts, and it should be doing 100 watts there. So there's something seriously wrong there. Now I'll go down to 10 megahertz, and I'll select FM mode there at 10 megahertz and see what RF power it does at 10 megahertz. But looking at it, it's not even registering on the test set. So at 10 megahertz, we switch frequency to 10 megahertz dead roughly, and we should be getting on FM with the TX power pot wound to the far left, we should be getting 5 watts, and we're only getting 1 point something watts there, I think, out with the look of it. It's not much power at all, that 1 point something watts just here. Okay, so I'll go on to 14 megahertz on FM. Again, we should be getting 5 watts there, so wait for the test set to catch up. And we're only getting milliwatts. Let's try 25 megahertz there, 24.979. Just make sure it's on FM. Let's see what it's doing there. A couple hundred milliwatts, if that. Now, the current, quiescent current that the radio seems to be drawing has now escalated to 10 amps continuously, which is very concerning. And so if I just put my hand, yeah, it is hot. It's not hot enough to burn your fingers, but I'd say it's warm, very warm, and it's warm on the left here and normal temperature on the right. So it does seem to me like as if it's RFPA related, because the power amplifier is in that area. So let's have a butcher's now at the board itself with the lid off. Let's have a look. Okay, we've got the lid off, but then we've got another lid underneath, so we'll just unplug the loudspeaker, which goes into there. I believe that to be the cable for the loudspeaker, so we'll just disconnect that, and then we'll just remove these screws here, because the PA board is just under this panel. So we'll just go through removing all these screws, and there's quite a few of them by the look of it. I don't want to take the speaker out if I don't have to, but looks like as if there might be, not sure if all the screws are the same. They look like it. So I'll tell you if there's any long screws or short screws that I managed to get out, that are obviously, if there's any differences between them. But so far so good. They're all the same type of screws. There's obviously one up there in that corner as well, and this one here, and then another one. I think there's one under there as well. I think so. Is there? Nope. Just get rid of those screws. And then this one here. And there's two there. There's a few on it. Big metal panels. No plastic, fantastic. It's all good stuff. Right, see if we can lift this lid up very carefully. Just make sure there's nothing else there. And we're okay. We've got the loudspeaker on the bottom there. We can discard that now to one side. Okay, there we are, the PA stage. So makes you wonder what will be wrong with it. So we'll have a closer look, I think, at the board, see what we can see. So there they were the suspects on the other, these two, because they had a diode. If I remember rightly, it's in the Kenwood TS2000 video. If you look at that, this is the fault we had with that after we did all the fault diagnosis. If I remember, the TS1972 is a transistor that can also be used as a line output driver for a TV CRT cathode ray tube line output transformer, or what they call a flyback transformer. It generates the EHT voltage to the cathode ray tube, obviously to produce, you know, the 10 to 20, 30 kV, if it's a colour TV, for example, high voltage supply for the cathode ray tube. So in order to prevent the flyback transformer's primary windings from stuffing the transistor, they employ a diode across the collector emitter junction of a transistor, integral within the RF transistor, because these transistors were used heavily in CB radios at 27 megahertz since 1980s, 70s, when they first came out, these TSC1972s. Same with the TSC1969s. But they were a dual mode transistor where they could work as an RF transistor in the HF frequency range, but also as a switching transistor for things like line output transformers, flybacks, things like that, laser drivers, all sorts of things like that could be done by these transistors, as well as being RF amplifiers. So they had the integral diode in them, which in the last video I did on the Kenwood TS2000 repair, if you remember rightly, when we tested the transistors out of circuit, from what I remember, the diode had gone low resistance, if you like, both ways. It had not shorted completely, but it wasn't far off. But in that case, it had popped the 4 amp fuse. There was a 4 amp fuse that supplied voltages to these transistors for the collectors, and if I remember rightly, that fuse had popped. So it was a fault with the transistor, and it sort of came and went as well, did the fault. And we thought that it was a build-up of conductive flux between the collector base and emitter, and we thought that perhaps the voltage on the collector was leaking across the flux residue onto the base, and thus biasing it on partially, and that made it conduct, because the current came and went. It sort of was there 1 minute, the quiescent current, drawing a lot of current and obviously cooking it, and then a moment later it was back to normal, and it was sort of just as we were cleaning the pins. But anyway, when we took the transistors out and put them in the transistor tester and tested them, we saw that the transistor tester showed that there were one of them was faulty out the pair. So this could be a repeat of that, and it's very similar fault to that Kenwood TS2000. So it'd be interesting to see. I think the next thing we need to do is just look at the circuit diagram now to sort of understand the function and how it works. I mean, I don't think it's self-oscillating, but I'm not 100% certain yet. I don't think so. Not with the characteristics of the measurement that we've just done, showing by changing the bands from one band to another, and the ATU here switching in different parts of the LC circuits there, it would have changed its current consumption at that point because of a self-oscillation. would have been dampened to some extent by the LC switching in the ATU. It would change its impedance on different frequencies, and it wasn't doing that. So I am looking around this area or that area. It could also be a fault in the biasing circuit. The RF transistors might not be working properly because of the biasing. It could be off. It could also be, if you remember when we were looking on the radio test set a moment ago, when this should have been doing 5 watts on low power, it wasn't. It was doing a couple hundred milliwatts. So there could be a bias issue, or it could be low RF gain on one of the transistors because it's breaking down its transistor junction, because it's in more or less full saturation, full conduction, because of perhaps an external fault or even an internal transistor die fault as we had on the Kenwood. So yeah, I think we'll have a look at the diagram and just try and understand a little bit better now of how this circuit works. Okay, just reading the RF circuit theory of operation here. It's a little bit pidgin English is this manual, but we'll try its best. It says the RF circuit amplifies operating transmitting frequency to obtain 100 watts of RF power output. The signal from the first IF mixer is passed through the low pass filter unit L1402, 1403, C1405 and C1409 and amplified at the RF amplifier RFB unit IC1401. The amplified signal is amplified again at the wideband YGA amplifier, again within the RFB unit, being IC201, after passing through one of the 10 bandpass filters. And also it talks about a page reference to which bandpass filters are used depending on what frequency you select, and high pass filters. So it uses a combination of bandpass and high pass filters, and is then applied to the PA unit via J201, which is this coaxial cable just there. The signal applied from the RF8 unit is amplified at the pre-drive Q1, which is this transistor down there, and Q2 and Q3 transistors, power amplifiers, and also then Q4 and Q5 transistors, power amplifiers, in sequence to obtain a stable 100 watts of RF output power. The amplified signal is applied to one of 8 low pass filters in filter A unit, which is obviously one of these two. And that's all it says on that. It says sod all else about anything else on that. But if we just go to the circuit diagram now, we'll have a butcher's at that. But yeah, we can obviously see the supply voltage 13.8 volt for the whole radio from the power cable here. The socket on the back comes straight in and connects there. So that'll explain why when we've not got the radio turned on, we're getting current draw, because power's applied to these transistors all the time, even when the radio's switched off. You know, so that's always needs referring to. It is protected by a fuse, obviously. On some radios it isn't protected by a fuse, but yeah, you should always make sure your fuses are the right ratings, because if you left a radio unattended, it would develop a fault. It potentially could catch fire if it's across the supply rails, so always got to bear that in mind. But hopefully if you've got a fused line, which you should have, it should protect it. So yeah, we'll just have a look at the that circuit diagram. Okay, just thought we'd have a look through the circuit diagram now for the RFPA. So we've got low level RF signal coming in to the connector at the bottom corner. If we saw earlier on the last shot where that was, that grey coaxial cable, it enters in there. We've then got a pi attenuator consisting of R1, 2 and 3, which form the pi attenuator to reduce the RF signal level down. Again, it's only low level signal in the order of probably tens to maybe a couple hundred milliwatts, if that, coming in. It then enters L14, which is an RF transformer. On the primary side, it transforms across then to the secondary side. With then the signal path then continues to be across a parallel resistor, 220 ohms to ground, and then a series capacitance, 2 capacitors in the RF path to the base of the transistor. The base of the transistor's got a DC voltage level indication where it describes 0 volts for RX and 1.77 volts for TX DC on the base, and this is obviously provided by this line here, by these two series resistors. So we'll look at the bias circuit separately shortly. We've then got what appears to be a feedback loop here from the collector to the base for RF, for its negative feedback, for linearity. So that's there, and we've got on the emitter here on the transistor down to ground via a 4.7 ohm resistor, and then a capacitor there across the emitter to on the common emitter to ground, so that the RF voltage swings on the collector and we don't get RF voltage swinging on the emitter, but will allow the DC bias conditions to be settled through the emitter. Then we've got here this red line here. This is a supply voltage with the look of it coming in, so we'll just trace that back. Yeah, so this is the main supply coming into the radio, bolting to those two screw terminals on the RFPA board. Obviously the negative to the chassis of the radio, the positive carries on, splits off to a fuse to supply relay and power circuits down here. We've got some reverse protection capacitor across it, and then it comes along as highlighted by red, and as you can see it branches off to many inductors as it goes along. But first of all we'll just describe the part of the circuit we were dealing with, and that comes up here to the inductor, which looks like a radio frequency choke L2, goes through radio frequency choke L2 with some parallel capacitance to ground for snubbing off any RF. It then comes up here to the bottom of this transformer, and also carries on this way via a 220 ohm resistor to the collector of a transistor. But similarly it goes round the low impedance path of the transformer, comes over to the collector and supplies the 2SC1971 as per the voltage diagram here, both in receive and transmit mode, so it's live permanently with 13.8 volts. We'll look at this center tap thing in a minute because I'm not sure what that is yet. Likewise, the RF signal then from this primary side of this transformer goes on to the secondary side of this transformer, which is L1, and then the RF level then gets derived into both these transistors. These are 2SC1972s. Now I'm just looking here, we've got, as we said, the tap at the bottom of this transformer carries 13.8 volts through it, obviously to the collector, because then the swing is on in the coil. So as the RF signal is amplified, it swings on the coil, and thus it transforms across then to the secondary winding. But this center tap doesn't look right to me. It comes off down here, goes through a big electrolytic capacitor, which I doubt that would be in that part of the circuit there anyway. It comes into another inductor. This diode here is the diode that's fastened mechanically by a heatsink compound to the casing of the transistor, so that as the transistor warms up it adjusts the biasing automatically. And we've got a potentiometer which then comes down to here and goes that way. So I think that's a typo, that, because if we look at these two transistors again, we've got from the main 13.8 volt supply line, this red line, we've got supply going via this L5 radio frequency choke. It comes up to here via R17, which is a 10 ohm resistor, goes up to here and arrives at the center tap of this transformer, and then from there it goes south to the collector of this transistor, which is obviously a 2SC1972, and it also goes north to this transistor, again 2SC1972. Both of these transistors are common emitter, as by the symbology there. We've then got 1/2 of a potential divider, which is R14 and R13, between the base and ground. These two circuits here that comprise in via R15, R16, C11 and C12 are linearity RF feedbacks, negative feedbacks, the RF conditions, the AC conditions, not DC. And yet when we look at this voltage diagram here, it says RX 0 volt, TX 0.68. Well, there's no way in a month on Sundays that you're going to get any DC voltage on there, because there's no bias connecting to that, and there's no resistor connecting to it, you see, from a supply. However, this looks like as if it should be the bias that's connected to the right side of the transformer, not the left, because as we can see here, we've actually got a voltage that will be an input coming in via the potentiometer. We've then got this part of the circuit here with this diode clamping the voltage, obviously. This diode here is laid across one of these transistors and coupled to it with silicon heatsink compounds. As the transistor warms up, this silicon junction in that changes characteristics and adjusts the DC bias appropriately. As there are 3 diodes in the circuit in total which do that, and I'll describe the others shortly. So I think this diagram must have been drawn on a Friday afternoon at Icom before they all piled out the door to the pub. Maybe they could have done the other part of the diagram before they went to the pub, but this part of the diagram was done after they came back from the pub perhaps. But this centre tap here is a bit weird because it doesn't show a centre tap on the transformer. If we look at these transformers here, we can see the black dots on the centre taps. So I don't think they've drawn that right, but I'll stand corrected if I'm wrong. But I think that should be on that right side. Maybe there's an amendment to this diagram, a revision, which I might be able to find. But there's definitely no bias applied to that, even though the DC diagram there, the indication shows there should be. So there's definitely an error in the diagram there, beyond doubt. Anyway, we'll carry on. So again, we've got that supply obviously going off again via another inductor, 13.8 volts going through this RFC up to here via that to the center tap of there. We can see there getting supplied. The RF again swings on here, push pull, because obviously this is a big RF transformer. We then get the RF transform to the secondary winding here on L4, and again splits off 2 ways. There's a signal path to these 2, what are the big pill coloured, white coloured big power transistors bolted together at the back end of the circuit there. And again, the biasing conditions for these are fed through this centre tap on this transformer, again deriving via this RFC choke L22. And because it's a high current that these 2 transistors need for DC bias, there's Q8, which is a 2SD 1585K NPN transistor, again gets its collector voltage from the 13.8 volt line via a radio frequency choke to the collector of a transistor. The emitter then follows up then to what is the center tap of this transformer to supply DC bias to both transistors as per the DC diagram there, the voltage diagram, saying that we should have 0.65 volts DC on transmit on the base of these transistors. These 2 diodes here are again directly mechanically laid across these 2 transistors, this Q5 and Q4, the big pill white transistors, and there's some silicon heatsink blob on them, which allows these diodes to get coupled thermally as these transistors warm up. So then they'll adjust the biasing proportionately for these 2 transistors. The 2 transistors finals themselves have got a larger radio frequency transformer, which is the big black transformer we were looking at on the board earlier. Again, that has a center tap, which then has a supply voltage fed through an RFC. We've got some smoothing electrolytic caps and some choking off of RF there, and DC smoothing. Again, when we follow the line down, we've got a current measurement that can take place across a 5 ohm resistor or a 0.5 ohm resistor, and then it goes straight to the DC supply coming in. So obviously that's the high current proportion. That's where we get the 20 odd amps current absorption through these components when it's, you know, transmitting at 100 watts full power. Yeah, so going back to that a second, I think there is a problem with the drawing there. I think that line should be on the right side, because obviously there's no way these transistors can receive bias voltage unless there is a center tap on the right carrying the bias current. and that would be correct, but in its present drawing it's not correct, so that would presumably be the reason why. So again, we've got down here we would have the bias set by this potentiometer and this temperature compensation diode, and likewise here for the final output transistors, these two big transistors, the biasing conditions for there are set by this potentiometer R18 and these two diodes D2 and D3, and they would temperature compensate individually for each of these transistors. And that's about all she wrote. Obviously we've got a fuse 1 here, and that goes down to a relay, and obviously power circuits are derived, so when we turn the power onto the unit, that's the main power relay, with some of the DC switches for receive and transmit down here, which form the biasing arrangement, and the fan control, temperature control for the fan, that's all done there. And then with some voltage regulators here, these IC1, 2 and 3s. These are obviously the main supply voltage regulators for the different rails in the radio. We've got 8 volts and 5 volt rails, 2 5 volts and 1 8 volt with a look of it. So that's all she wrote. Obviously the RF output from the two finals on the power amplifier transform across from primary to secondary here on that RF transformer, and then come out on a socket, then off to the RF filter unit and the ATU, automatic antenna tuner. So that's all there too. So I think the next stage is to look at these voltages to check that the base of these transistors are getting this voltage here that's defined by the TX voltages, and likewise on these two transistors here, check the bias on there. We'll look at this as well on the actual circuit itself to check where L3 and these caps are junctioned probably to the right side of this transformer. I can verify that anyway, one way or the other, but I definitely think that's a typo. So there we are, that just about describes it. Okay, we're almost ready now to do some measurements with the voltages. So basically this is a 2SC1971 transistor, which is a pre-driver, and then with two 2SC1972s as per the diagram that we've just gone through. These are the RFPA transistors. That potentiometer there controls this transistor down there, which alters the bias for these two, and this potentiometer here controls this transistor, which then sets the bias for these two devices. So what the advantage of this measurement is to prove whether or not the transistors are getting the right bias, what bias they're getting, and let's see which one of these three transistors is maybe conducting all the time. Is it conducting because there's a fault condition within the transistor itself, or is it conducting because the bias pots have been messed about with by the previous user, or perhaps there's a fault in the bias circuit? It may not be an RF fault, but who knows. That's the reason why we're doing this test. So we've got the multimeter on the top right left hand side of the picture connected to the radio chassis for the 0 volt connection. We have obviously the pin out for the transistors like base emitter collector. That's how the transistors are configured from left to right. So what we'll do, we'll connect power now, and then obviously I'll just look off camera to see how much current it's drawing. It's drawing about 5 amps at the moment. So we'll obviously go on to the 2SC1971 pre-driver first, and we'll just have a look there to see what voltages there may be. So we'll just go on to the first pin, and there's nothing there basically, it's just millivolts. We'll go on to the center pin. Obviously that's the emitter down to ground, so the base has got nothing on it DC wise, the emitter nothing on it. Obviously you shouldn't expect that, and on the collector we should get 13.8, and we are doing 13.92 volts. So let's go on to the driver transistors now, which are these two, and check those. So if we go on to what is the base on there, and just have a look, we're getting 781.4 millivolts DC drive there. and then obviously if we do the same and go on to that pin there, we're getting 925.3 millivolts. Well, I wasn't expecting that, simply because the fact that the transistors are provided with bias from the same device in the same circuit. They're not independent bias circuits per transistor. So had the devices not been faulty and the bias circuit perhaps be faulty, then both transistors would receive the same bias voltage. But because we're getting different bias voltages here, this suggests to me at this initial stage obviously needs confirmation that the transistors have got some kind of leakage internally within them. And now what we'll do, this potentiometer here sets the bias voltage, and we'll turn it. We'll turn this down to minimum, so that's not making any difference at all there to the adjustment whatsoever. Now that might only be present on transmitter, though I doubt it, because according to the diagram that I have, and that's set no matter what, whether you transmit or not, because the bias is set permanently. So it's 778, and turn it up, and it is varying just ever so slightly. The current is now creeped up, so this bias control is not having any impact whatsoever on the measurement. Now if I just feel with my finger on the transistor to see which one's getting hot, that does feel quite hot, that transistor there. The tab of that is almost burning my finger, and yet the tab on this one is stone cold. There's no temperature at all, so that transistor's cooking itself. If I touch the driver transistor, there's obviously no heat there at all, but that is really hot, very, very hot actually. And the current's going up all the time. So what I'm going to do, I'm going to disconnect the power now, which I've done, so we're not going to cause any destruction of anything, because obviously it's starting to rise as a current, and we'll get to a stage where that goes fizz bang. So I think it's time now, now we've established that the potentiometer here doesn't adjust the bias at all. It seems to me that this transistor really isn't supplying any current of any degree to these two devices to cause that fault condition. This transistor is not even warm, it's stone cold. So that proves to me that if the bias circuit was faulty, it would be providing too much current to drive these two transistors with DC bias, and thus potentially this would start to heat up, and it isn't doing. And also the adjustment of that pot up and down means no matter what this transistor is doing, what voltage it's supplying up and down, is not making any difference on these transistors at all. So I think it suggests at this stage, again to be confirmed, that there's some leakage internally within the transistor from the collector to the base, and current's leaking across to the base, which is then being fed to the other transistor as well. So potentially it could be the one that's cold may not be working either because it's failed, or it could be that that single transistor there is leaky within its junctions and also partially working with RF as well, because we were getting a little bit of transmit power earlier but very low levels. So again, could be both transistors are packed in. The only way now to proceed is to remove the transistors and test them in the transistor tester to see what the HFE values are like and what the condition of the junctions are like within the transistors themselves. That will then tell us whether or not those transistors are defective. Also, we can do another test where we remove the transistors, and providing the traces are nice and clean and there's no bridges of solder in that removal process, we can turn power on to the radio again and see whether there's any further current draw, which will rule out any other circuit that's related with the function of those transistors. So that's something we'll do now. We'll just get them out and give them a test. Okay, so just a hint on the removal. The screws that hold these two in don't have an insulating washer, but this transistor does under the screw. So just be careful if you have to replace one, because you can see there that it's got this insulating washer, and that goes on the 2SC 1971. So we've got the desoldering gun here, jazzed up, ready to go. We'll just remove a temperature sensor and pull that to one side. Now you can clean this crap off it because it's going to obviously get very dirty. It's silicone heatsink compound, it gets absolutely everywhere. It's one of these things that it's like paint. No matter how you try to keep it off your clothes or whatever, it'll always end up on there. So I'll just clean this off because this stuff's awful. It's everywhere, and you can be as careful as you want, but you'll never get it 100% off without getting some on you at some point, or on your toes. Look, it's already on my fingers now, and I haven't even touched it with my fingers. So clean that off, and then might stand a chance at removing it without messing everything up. So we'll just remove that. Get some more solder off it. There's plenty of solder on these pins. You're best off removing the screw from the center tab anyway there, because when you solder or try to unsolder the center pin there, the heat will dissipate through to the tab and then dissipate it into the heatsink, so it'll make desoldering that very, very difficult otherwise. So we'll go on to the base now, remove that, just back onto this central emitter here. Right, what I tend to do is I just pick them up off the heatsink a little bit using a little pry tool that I've got, which is hiding itself at the moment. Now I need it, but anyway, screwdriver will do. Just very gently lever it up so it's a bit loose, and then what you can do, if you just pull against the tab ever so gently and then go on to the very first pin or one of the pins and just lever it just ever so gently. Try and get across 2 pins at once. If sometimes you drop on, the pins will come away on some transistors very easily, and you'll be able to remove it quite simply. However, on other transistors, unfortunately, like this one, it's becoming more troublesome. So you have to have a little bit of patience with them and not try and rush it, and certainly don't try and jar them off the board, otherwise you're going to end up damaging the PCB. This one is the more awkwardest that I've removed in some time. There we go, look. Eventually it comes. It depends on all the solder is as well on them, because sometimes the solder is 20 odd years old, especially on really old radios like 20, 30, 40 years old, depending on the age of the radio, and so the solder itself has become quite tarnished. So remove that, leave it to cool down a little bit, and I'll remove the 2SC1971 as well, so we can test that to see if that's doing okay as well. So right, on to the next one then, and this 2SC1972. I'm just going to prop the radio up a little bit so I can see it, because you might be able to see it with a camera, but I damn well can't with my angle here. So right, I've got that there. Right, okay, so we'll just zoom in a little bit more so you can see. Right, okay, onto this one now. Again, just lever it just slightly, just so it removes its contact, its thermal contact with the heatsink. Sometimes it sort of gets stuck down, you know what I mean, and you can't get them to shift. Right, that's that one done. And then centre pin. Of course, before you do this, always remember to disconnect the power. I know I've seen plenty of texts over the year forgetting to disconnect the DC power, and then they go in with a soldering iron trying to unsolder the transistor, and then it goes fizz bang, obviously, because you're bridging the connections. And if the multimeter, the soldering iron rather, is on the grounded to the chassis side of the power supply, you know, the neg VE line, then basically it will short out the collector on the tab of a transistor. So I'm just trying to get that thermally going. A lot of the heat from the soldering iron gets dissipated. I'm trying my best not to cause any damage, you see, to the PCB itself, and trying to get the solder to flow. Sometimes in order to remove them you need to add more solder, and so by adding more solder you actually stand a chance of being able to lift the pin. It's just one of those things, so you can do that as well. So I'm just trying to flow it again. It's well and truly stuck down, is this one, so we might have to do that. I might have to put more solder on just to get it flowing, because it ain't coming up, is this one. It's been an awkward devil. Some radios, they come off like, you know, within seconds you can get them to come off. Other radios, there can be a devil to shift. So we'll just put some new solder on just to flow it, get some flow there. And I've even had it in cases, some cases where they've what they've done, they've actually Loctited the transistor down as well. They've actually put Loctite under the leads as they just touch the PCB board. And this one's really difficult to shift, this, in comparison to other repairs I've done. There we are, look. So that's another technique, being able to remove them, is to put a bit more fresh solder on, brand new solder, after you suck the old crap off, and just scan up and down by going up and down with the soldering iron, just to flow all 3 pins, and then get the transistor to come off. That's still really hot. But the main thing is to remove a screw that fastens the transistor down, so then when you get to the center pin with the soldering iron, the heat doesn't flow straight through. The center pin's internally connected or bonded to this heatsink tab. So if that's fastened down to this heatsink underneath, then all the heat's going to get wicked away, and it's also going to wick away the heat from the other 2 pins as well. Not as much, but it'll still do it. Right, so remove that. And then what we'll do, we'll suck off the excess solder. I'll put some fresh solder on the others as well, the other pads, and then we'll remove that. So I'll just do that, just put some fresh on there, and again just here, ready for when we put the new transistor on. Obviously if you put too much on, you can remove it again. Like there's too much on this one now because I added it, so I'll just remove this. That's it, and that way then it helps when we're putting the transistor on the new transistor. And of course we'll clean that as well with isopropanol alcohol, just to make sure that the flux residue isn't remaining and thus become conductive, because some flux residues are conductive, especially aged flux residues, and it is a known issue on quite a few radios and electronic equipment that, you know, you can get flux that starts to conduct, or microglobules. As you can see, it's pretty nasty stuff, but because it's obviously leaded solder, this isn't lead free. This is in the days before lead free solder, so we're just getting rid of that now. So that's most of that gone, and it's just over to the 2SC 1971 now, so we'll see whether we can get that. You can clearly tell that's very old solder, it's tarnished, it's, you know, it's old, it's had enough as that, so we'll see if we can remove that now. Just see if we can. And my paste soldering gun has now got blocked up, so we just need to have the, which is arm's reach yet again, we'll need to unblock our solder sucker, because it's sucked up that much solder. It's actually got jammed inside. Let's see whether we can. Ah, that's better. It's no use losing suction. You've always got to have suction. So I'll just go on there. Nothing worse than a loss of suction. So again, just flowing that one, bubbling away nicely, and then this one, and we'll just give it a wiggle. Now again with this one, this leg here at the edge on the far right, which is the collector, that's moving. These are again stuck down. So again, you can apply more solder. This is easier than trying to pry it off, because obviously then you can damage the transistor itself, the legs. You can also damage the PCB. So I'm just going down there now, just putting some new solder on, and that way then that should resolve that issue. It's just there we are. And then what we'll do, we'll just race up and down the 3 pins there like this. Now as long as you've got hold of a transistor, obviously it's not wise to grab it with your fingers, because obviously you'll hurt your fingers, burn your fingers. So just go up and down and then see whether we can get this damn thing off the board, because it's again, I think this is one of these things when they're in the production run where they actually glue the package down to the PCB before the solder's applied, and I've certainly seen some Loctite residue as well on there. So now we've got the PCB traces there, to solder on them, so we'll just suck that off, and that's that, ready now for cleaning. Solder sucker's still working. I'm going to leave that to cool just a second while I then get the rag with some more isopropyl alcohol cleaner on it. Just give that a bit of a clean up. Pretty shame really that in the manufacturing process they didn't remove the solder flux, you know, after they'd put the transistor down. As you can see, even with this transistor and these on around the power transistors, a lot of solder flux residue left behind, which over years causes corrosion and other problems. So really they need to be cleaned up before we finish this repair today. So that's cooled down enough now. Right, we'll get the transistor tester out and we will see whether the truth of a transistor tester tells us what's actually wrong. Okay, so we've got the tester of truth here, our trusty transistor tester. I've removed the transistors and placed them here in the same orders that they were in the radio. So I'll remove this one first, then that one, and then this one. And I've actually got a new socket. This socket for this thing is a bit dicey. It's can't quite grab the pins very well, and it's a bit loose. But I've got a replacement socket here, which I found in my components drawer. It's got much bigger openings in it for the pins, so it can connect to things easier. But I just got to modify the this socket here with longer wires on it, and remove this socket here in the tester, so that I can hardwire that in, if you like, onto the PCB, and then what I can do then, it'll replace that older socket that came with it, and because it's a bit erratic, it's not exactly a good connection. It makes connection, it works, but it's not exactly the best. So, and it's particularly transistors like this as well, where the leads are short on the transistor, it can be difficult to get them in, because this is the thickest part of the lead. Normally the lead that protrudes beyond the normal length here goes thinner slightly by a few microns, so it makes it quite hard to get the devices, when they're that short of pin, into the transistor tester. Right, so we'll hit the switch and test the transistor now and see whether it's working. So it's testing. Oh, that's good news. So it's identified it's a bipolar junction transistor, NPN configuration. It's given us there the pin out, pin 1, 2, 3, base emitter collector, the HFE value, which is not particularly wild, but it's good. The VF for the base emitter junction is 784 millivolts, and it's already picked up there, as we can see there, the legend between the collector and emitter, the integral diode. So that's good news. So that seems to be a working transistor. So let's have a look at the other one now. and we'll remove that. So that's a good one in theory, and we'll just connect this one up. Again, that's a little bit, the centre pin's not particularly good on that one. Hopefully it'll go in and connect. Right, we've got it connected in. Right, we'll hit the switch and see what this one says. Testing. Ah, well, that's not good, is it? Capacitor. Is that because it's loose in the socket? Let me just re-fasten it into the socket. It's got a good purchase, so I don't see why it would be, considering it is a capacitor. So let's test it again. Sometimes you can get erratic results with these things. Yeah, it's thinking it's a resistor, so that's not good. We could do some independent tests now with our multimeter as well, just to verify that the tester's not telling me pack of lies, but I doubt it's lying, the tester. But we always try and verify things. Yeah, it keeps coming up with the same sort of thing, so let's just test again. I've moved it a few times now, and in the socket it's not the socket or anything, and yeah, unknown or damaged. Yeah, it's having trouble trying to identify it now. I think it thinks it's a resistor, so it's having trouble. Yeah, keeps commonly coming up with that, so yeah. So we'll remove that transistor then. So that's suspect knackered. Then we've got this transistor here, which was the pre-driver, if I remember rightly, and put that in the sockets, shut it down, and then hit the test button again on this one, and let's see what that says. Yeah, so that's identified of a nice working transistor there. HFE, again, much higher than the other transistors. 2SC1972 has been 30 something HFE, whereas these are 64, almost double the beta and the HFE. So the VF on that is 783 millivolts or thereabouts. Again, it's a NPN, a bipolar junction transistor, and it's identified the integral diode, as you can see there. So I'm quite happy with that. I think what we'll do now, we'll do some tests using the multimeter on the transistors to verify these results on this multimeter now. So we'll do that next, just to double check. Actually, I forgot I picked this up at rather a great expense some time ago. This is a component analyzer by Peak Electronics. I've got various ones of them here. Made in England, you see. Very rarely see that these days. Anyway, I'll just connect this up to this this transistor, and we'll see whether or not, you know, we can get any truth out of this. And Bob's your uncle. Right. So let's see what this tells us then. Ooh, a silicon transistor. Alright, scroll is on. So it's telling us the base emitter collector leads, diode protection between collector and emitter. It's identified that again. Current gain HFE is 32. So I believe that's what the Chinese cheapo tester told us, and tells us some more detail that the other tester can't tell us. The current, obviously the volts base emitter, 0.69 of a volt, whereas I think that said it was 0.72 something, the other transistor tester. So it's not far away, you know. Current base 4.6 milliamp. Current collector there, it says leakage current, there's nothing there. NPN silicon transistor, so that seems okay. That's the original one, the first one we tested, and that seemed to be okay. And I told you silicon heatsink compound gets everywhere, and indeed it does. So we'll connect up to this one now, and let's just hope this one verified as defective like it did on the earlier transistor tester. Of course you can use a multimeter like we were going to do, but I thought I'd use this. I paid a lot of money for this. It robbed me blind when I bought this, so I've only used it a couple of times on these repair videos, so it's always good to see it working. Ooh dear, unknown faulty component. Right, scroll's not working, so it just basically says that's it. That's it. The roller shutter door comes down, unknown faulty component, goodbye. That's it. So yeah, that's definitely stuff then, isn't it? Alright, so that confirms what the earlier transistor tester found, and we'll just get rid of the that one, and we'll connect this up to this transistor tester. This was a pre-driver, and of course the peak testers are calibrated, you know, top of the range sort of tester, that industry standard thing that's used, whereas this is a Chinese knockoff sort of thing, you know, that you buy from eBay or whatever. But it still works, you know. But it used that, but I splashed out for this. I do have other testers that are more advanced than this as well, but they take up a lot of space in the video, trying to get them in the camera shot, whereas these little portable devices are nice for things like that. So again, identifies the leads, what's connected to what on the transistor. Diode protection, it's identified between the collector and emitter. Current gain rather, HFE value is you know, 54. Can't remember what it said on the other tester, what the HFE gain was, but I don't think it's far off. IC 2.5 milliamps, base emitter voltage 0.73 volts, and then again current base, leakage current, and then NPN silicon transistor. So yeah, back to where we were. So I'm happy with that. Sort of understand now what's going on. So we'll just have a look at that other transistor now on the multimeter, this one that's stuffed, and we'll see what reading between the pins. If it's anything like the one that we had on the Kenwood TS2000 on that repair video, which you'll find on my YouTube channel below, there was just a low ohm resistance between, I believe, a collector and emitter. So yes, interesting. Okay, ready to do some testing now, these transistors. We've got the multimeter set up on diode test. We've got the three transistors here, the 2SC 1971 and then the two 1972s. So if we just look at the package style a moment, we've got obviously the package like this, and then we've got the legs coming out, which will be, in this case, base, emitter, collector. Obviously the symbology for this NPN-BJT is base, collector, emitter. And if you remember earlier in the video, we were talking about the integral protection diode, which is inbuilt within this basically. So we have an inbuilt protection diode in the collector emitter junction path. So that protects the transistor from back EMF, from different types of applications that it can be used in. It's not just used in RF, it can be used in RF heating, or it can be used to drive a flyback transformer or an inductor or something to generate high voltage for, say, a cathode ray tube. Now within the transistor as well, the tab, the metal tab, the heatsink tab, is connected electrically to the emitter lead in the centre of a device as well. So that aids us in doing measurements where we can connect to the tab instead of trying to get on the pins, especially when the pins are small and cut short like they are here. So what we'll do the testing where we're going to check the forward voltages of the junctions of the transistor. So we're going to make the base positive and the emitter negative. We're obviously going to test that both ways round, and do the same with the collector base junctions, and then of course the integral diode within the transistor. So we'll start with the 2SC 1971 first, and we'll make the emitter negative and the base positive to check the forward voltage of that diode path, that part of the transistor junction. So okay, we're going on to the base and emitter. As you can see on the meter there, we're getting a forward voltage of 646 millivolts, which I'd expect, but if I reverse the connection, so we're making the emitter positive and the base negative, we shouldn't get anything. So that proves that junction's okay. And then Now we need to go between base and collector. So if I make the base positive and the collector negative, if I can get on the damn thing because the leads are so short. Okay, so we're getting a forward voltage there of 640 millivolts, but we shouldn't get anything the other way around, where we make the collector positive and the base negative. And as you can see there, we're not getting any voltages. So that proves that junction between collector base and base emitter is all working fine. The last test now is to just test between the collector emitter junction. So if I make the collector positive and the emitter negative, we shouldn't get a reading because obviously the integral diode is the reverse. However, if we make the emitter positive and the collector negative, we should get the diode reading. So that proves there that the integral diode, protection diode across the collector emitter junction is allowing 631 volts, 631 millivolts for voltage. So that's correct. So that transistor's okay. So we've checked this integral diode. This is now a ICOM756 So again, same principle again. We'll make the base positive and the emitter negative. So we'll go on to the tab being the emitter and the base being the left pin. We're getting 611 millivolts forward there, but if we reverse it, we shouldn't get anything. And we're not, which is good news. Okay. This time again, if I make the base positive and the collector negative, we obviously get the reading, 601 millivolt forward, which is correct. However, the collector, we make that positive and the base negative, we should not get a reading that way. Again, now we're testing the integral diode, which is obviously the collector emitter. So if I make the emitter negative and the collector positive, we should not be getting a reading, and we are not. The pins are so difficult to get hold of. And then, of course, if we make the emitter positive and the collector negative, then we should get a reading that way, which proves the integral diode is working between the collector emitter junction. So that means that these two junctions and the integral diode are okay. So that rules that out. So this must be the faulty one that we were looking at on the transistor tester. So we'll prove that now. So base positive and emitter negative. And we're getting a much lower forward voltage now of 213.4 millivolts. If I reverse it, we shouldn't get anything. So I'm making the base negative now and the emitter positive, and again we are getting a reading which we should not be getting, 225.5 millivolts. So that's leaky. It conducts both ways between base and emitter. Doesn't matter which way around you go, you know, with the probes, one way or the other. Okay, so let's make the base positive and obviously the collector negative, and we're getting 92.7 millivolts, again way low for where it should be, and we shouldn't be getting anything the other way around, and we are 93, so it reads the same both ways round. And again between collector emitter junction, which will then test the theory about the current draw when we had the quiescent current of about 4 or 5 amps up to 7 amps as the thing warmed up, being sunk by this transistor. We'll just check this integral diode now. So if I make the emitter negative and the collector positive, we shouldn't be getting anything, and we're getting 301 millivolts forward there. If I make the emitter positive and the collector negative, again, we shouldn't be getting anything there rather. So yeah, if the emitter is negative and the collector's positive, then again 301 millivolts there, make the emitter positive and the collector negative, and that's when we should be getting a reading, and we are. So in the case of the emitter being negative and the collector being positive, this diode should be working, and it isn't, it's leaking. So allowing the forward voltage to come across from collector to emitter and leak through this way through the diode. So yeah, bit of an odd one I'm afraid, but that's definitely a faulty transistor. It's better to replace them in pairs, even though this transistor is in theory testing okay. We'll have to compare the HFE value of this old transistor with the new ones when it comes. But in a push-pull application where these are used, it's always better to replace them in pairs. Not necessarily where they're from exactly the same batch, although that would be ideal. But as long as they've got similar HFE values, and they come from the same stock, as in the same year or month, so they're going to be fresh. You don't want one tired one and one really good one. So that would be okay, that transistor, again, to be reused in a repair later down the road when we'll need a single device to, you know, to replace. But whenever there's two working in sort of a push-pull, I always change them in pairs, even though one might be okay, because obviously that might be weakened anyway. And we'll, as I say, compare the HFE values, the beta values between the two devices when I get the new ones out the stock cupboard. So we'll have a look at that next. Okay, we've got the devices now out of the parts bin, the two 1972 replacement transistors, so we've got those. Before we reassemble everything, I've noticed as well that the heatsink compound that's applied to all these transistors and the temperature sensors as well, these diodes, it's very crusty and dried up, so we're going to wipe all this off and then renew that on all the sensors, including this one. It's all dry, it's not lost its sort of thermal conductivity properties, so we'll be getting rid of that and replacing it with some brand new stuff. I've got some really good quality silicone heatsink compound here from Dow Corning, and this stuff I use, so we'll be using this on these transistors. Now also, just for information, the driver transistor, the pre-driver, this 2SC1971 that goes here, there is actually a mica insulator washer there. You can't see it at the moment because it's transparent, but if I just move this camera in a bit, there is actually a mica washer protecting this surface, where there isn't a mica washer on the 2SC1972 drivers. Now the reason for that is we'll see on the circuit diagram now, is that this is the pre-driver, and as you can see there is actually an RC network in the emitter. So the resistor that's here in the emitter leg is for the DC conditions, and the capacitor is to then suppress the RF going off the emitter. So we don't get RF basically swinging on the emitter as well as on the collector. We only allow the DC path to go through the resistor and obviously set the DC conditions in line with the base, whereas the RF conditions, we need to make sure that the RF swings on the collector. So we don't want any RF at all present on the emitter, so they have a capacitor down to ground or chassis, or RF ground as it is, so that it ensures that RF remains at pretty much zero potential on the emitter and it swings on the collector, whilst allowing the DC condition to be set by that resistor. So there's two things really on that transistor, which we'll see when we reassemble it, but basically there is not only an insulating washer present on this surface to prevent the tab of a transistor from connecting, because obviously the center pin there is connected internally within the transistor to the tab, the metal tab that bolts here to the heatsink. So in order to insulate that, the emitter junction on the transistor, they employ this mica washer, which is barely visible. It's sort of just hiding away down. It's stuck down with this silicone heatsink compound, we'll be able to shift it soon when we clean it. And then what happens is then there's also a nut that goes here with an insulating washer on it to prevent the nut from bolting, electrically shorting out the tab. However, there is no insulating washer on the 2SC1972 driver transistors or insulating washer on the bolts. So when we reassemble later, we'll just have to take great care to make sure that the bolts for the 2SC1972 don't get muddled up with this one. Otherwise, you know, that's an easy mistake to make. So the heatsink compound on these is all old and terrible, so we'll clean it all up, and likewise we'll do the same with the PA transistors here for these temperature sensor diodes, and just make it nice, put some nice new silicone heatsink compound on, and that should help things a lot. Back soon. Yeah, so I'll just yank at this now, because it's ready for coming off. There we are, look. There she is. So we'll give her one side, and just I'll just get some washing compound on it and give it a bit of a scrub. Get rid of all that contamination that's on there best we can. And we'll go back to the diodes in a minute, because it'll be messy when we do the diodes, because obviously they're caked up in the stuff, you know. So let's see if we can get the worst off. Really, can use a cotton bud obviously as well. I've got some of those here, and we might do that in a moment. But just get the worst off. At least there's no old silicone heatsink compound there. That's the main thing. And then on the conductive surfaces, or the heat conductive surfaces. So that's that. And as for this diode, well, this is where I'm going to get caked up in the stuff now. But as you can see, it gets everywhere. Just silicone heatsink compound. Just one of those things where you can try and keep it off your skin, but good luck. It gets on your clothes, it gets on your skin, finds its way onto surfaces everywhere. It's terrible, terrible, terrible stuff. And it contaminates all the components that are around it and everything. So we'll probably use a cotton bud on that. Actually, I've got some here. And likewise with these devices here, give them a clean. This one shouldn't be too much of an issue, because we can just pull that away, but as you can see, it's pretty disgusting, is that one. Yeah. Just give it a wipe, get all this off. Yucky yuck. There, it's a bit better. And just clean away all this on this transistor. It's definitely dried up as that. Awful stuff, really is. I'll be seeing part number of transistors in a minute. And it gets everywhere, it really does. I'm just going to get some more tissue and some more rag. See whether we can clean that up a bit. And they go everywhere. So I'll have to get a cotton bud out now and wipe it all up. Horrible, horrible, horrible stuff. But we'll just get the worst off anyway, and then we can move on, can't we? We can see what the best results are going to be. So I can lift that off, lift that out of the way a little bit. Just get to the worst. Not a nice job at all. Soldering iron on this sensor in a minute and remove it, so I can get down to it. So back in a mo when we've cleaned it all up. I've noticed as well on these transistors, the legs here that are soldered, particularly near the legs, there's lots of flux residue still around, so I'm going to wash that off like we've got here, flux bits. But it looks like when they were soldering it, they've caught these resistors here, which is okay, but it's a little bit how you doing. And again, they've not clean the flux residue off in between the, you know, the legs. Again, that goes conductive, or can do. Time to come. Likewise, you know, same here at the bottom. Transistor. Again, seems to be a lot of flux residue around here in between the pins. So I think it'd be same on the collector emitter. So I might renew the solder on these and clean it all up and make it nice again before we go any further. It's such a shame really that they've just not washed the flux away, flux residue. Okay, so I just want to remove some of the solder, and so I can get this thing off. Same here on this emitter leg. These are the emitters on the outside edge. Just got to get the heat flowing, and then once the heat's flowing, and then same on the base. And then just keep working this way around it, get nice and flowing. Same on the collector. Quite a lot of solder here. And on the emitter there. And do the same here. Just renew it, that's all. That's what we're going to do. We're going to put some fresh solder on. And we'll see what's what. Same with the emitter on this one. And same on this, like here. Sometimes the solder sucker thing gets blocked up when there's a lot of solder. And then you have to clean it out, you know, it can be a bit of a pain, but depends really how much solder's sucked up. There's quite a bit on these transistors anyway, so obviously we're going to have to do something there now. Just noticed, that's alright. Give that a bit of a clean, wash it with some isopropanol after we've put some new fresh solder on, so we'll do that next. Yeah, as you can see, I've just been cleaning this bit of a transistor here, getting the flux off, just so we can put some new on, and it's certainly coming off, which is good. Same on this one. Let's see if we can get the worst off, you know. Being careful not to damage anything while we're doing it, of course, you know. And then at least it's clean. Because nothing worse than old flux. Sometimes it stops the new flux from adhering, especially if it's, you know, ancient, like this will be. And then we can, you know, go on to doing the collectors. But yeah, you'd be surprised at just how much contamination you can get around these transistors, and they do get hot, and obviously they conduct a lot of current, you know, and they can bake the electrical connections quite easily on the legs, or you can, depending on the solder quality, if it's corrosive or the flux starts to corrode the solder joint because of the corrosive effect of the flux. So when we do resolder these, what we do is clean them thoroughly afterwards and not leave any thick solder residue or flux residue, should I say, on the pins. And Bob's your uncle, we should be okay then, but just trying to clean off as much as I can, because a bit of a devil, these transistors. If I get weird earth loops on them and resistance on the pins down to the emitters, if they're not got absolute good electrical connection, they can get some weird RF faults, and want to avoid anything like that. So yeah, I think that's looking pretty good. I think we're all sorted there on that one, and it's just the top one now. Got most of the flux off there. As I say, this is only a precursor to the solder we're going to put on them and renew. I use leaded solder, I don't use lead free, I use leaded, and the only time I use lead free is on newer devices that have got lead free solder. But I must admit, I'm a great fan of leaded solder. I'm not a believer of a lead free, really, but some people are. I suppose it all depends on your preference and what your methodologies are in repair, but I think there's a lot of problems with the lead-free solders, and I tend to use, depending on what components they are, I can use high melting point solders, so I tend to use that on power resistors and things that get hot, very hot, that are on power supplies or high voltage applications for valves and tubes, magnetrons, things like that, where we need to keep a good solder connection at high temperatures. So, and that's what I tend to use those solders for. But in this application, just standard lead solder will do it. I'm not too worried it's not going to get that hot, is this. So there we go. So I think we've just about managed to get all the flux residue off of that, I think, more or less. And same with these. I think we just need to give these a little bit of a wipe, and that way then it's all nice, all done, all ready for when we renew everything as it should be. Right, time to resolder. Okay, we're ready to resolder with our trusty soldering iron. And so what we're going to do is we're just going to resolder these components. I'm starting on the track at the side here. You might be able to see just at the very edge of the pins, and then what you do then, just as you get that going, as heat transfers, it starts to transfer not only the solder pads to the pin, but then onto the solder pad itself, and then we can just reflow that nicely, make sure it's connected all the way around the edge. So that's that emitter done. Then onto the base again, jointly onto the pad as well as the pin of the transistor, and then just start to reflow, put the solder in there, and then run it up onto the pin itself, so that what it's doing, it's making sure there's a connection underneath the pin as well as on top. So that's basically what we're wanting to achieve there. So again, you can see at the end there's some print, and then we've got the ramp up, if you like, to the pin. So I just start to apply to the print first, then move a soldering iron onto the transistor leg itself, and then let go. Don't stay on it for too long. The longer you stay on it, the more damage potentially you can cause to the transistor. Again, onto the PCB trace itself, just start the process of the heat transfer. You can see it moving along, tracking along the heat, and then move the iron onto the pin, quickly round it, and then leave it, and then just wait a few moments. Do the same again here, again onto the PCB trace, just start to get the heat going, because these transistors are very good at conducting heat away to the heatsink. Then move on to the pin and flow the pin back to the PCB, back to the pin, let go. Now some people stay on them for half an hour, you know, trying to get them going. It's best not to do that. If you're having problems soldering them, depending on what type of transistor they are, particularly these LDMOS multi-arrays these days, then you can back the screws off that hold the transistors down just a little bit, by about a turn, half a turn to a turn, and then but don't make the transistor loose in its mounting, because what happens is then when you torque the screws up, it'll break or strain the transistor itself, and that's the last thing you want. So it's advisable, really, unless you can avoid it, never to slacken off the connections, the bolts that bolt the transistor down. Now this collector is going to be quite interesting, because we've not only got the PCB trace itself to solder, but we also have this leg here that goes off to the transformer, the RF transformer. So we've just got to do 2 lots of soldering here, really, onto that one. And then likewise just here on this emitter on there as well, we're onto the PCB trace first. Just start the heat, and you can see it's tracking along, and then just flow nicely. Not too much solder, you know, we're not making a cake. And then again onto here, onto the PCB trace at the side, just start that solder running under the pad basically, and then along down the side, just a little bit more solder. You know, we're not looking for Mount Everest. And then again here on the collector again, and then we'll inspect the solder joints afterwards again, just to make sure that there's no short circuits or any solder slivers anywhere. And then the last pin here, which is this, you see you can get onto the trace at the side there, the PCB trace, and then just flow in. You can see the heat's trying to track across now, and then just a bit more solder round the front, and you're just guaranteeing that you've got that connection top and bottom as well. And we may as well just put a little bit of solder on these pads ready for when we put the transistor in place. So there's some nice new solder there for when we attach the transistors, and then we're not going to get any problems with those. And of course we'll clean them up again as well, so everything looks nice and tidy as it should do, ready for when we've obviously got the diode sensors and things to put back in place, and solder. This diode sensor solders to an RF ground emitters, or those transistors there as well, which we'll sort out next. So that's about it really for that. Right, so we've got these transistors all back with the silicon heatsink compound and the sensors on them. This one too. These two 2SC1972 replacements are in now. So we've just got the remaining pre-driver, which is the one that's the most difficult to put back in. So we're just going to put some silicon heatsink compound on this mica washer and just give it a bit of a rub round with the old finger there. Just get some on that side of it, and then we're going to drop that in place now onto the circuit board where we need it, in line with the hole. And then what we need to do now is apply some silicon heatsink compound to the actual transistor itself. And so we've got the transistor here. We're just going to apply some silicon heatsink compound to this. We don't want too much, just a little smidgen, and then we're going to sit that down on top of the silicone heatsink pad thing there, the mica washer rather. On most modern circuits you get these little silicone rubber mats to put them on. Now this is the most important thing. The screw for this one has got this insulating collar here, which is very important. So the screws for these two, although they're the same, these two don't have that insulating washer. So that's something to remember. So we'll just introduce that screw in just very gently at first, just so it gets its thread and then makes its way through the mica washer. Don't want to cause any damage. And just align the 3 pins then with the finger while you screw it down. So the 3 pins are there, and then just gently tighten it up. Now you don't want to tighten it up, it's not, you know, like Arnold Schwarzenegger sort of strength. We just want to nip it up just a little bit so it's tight, but not way tight, you know, just hand tight. And then same principles again as we did with the big PA transistors. Go onto the pad underneath, apply the solder to the pad, and then bridge it over then to the pin. Push down on the pin and then flow the solder. Don't stay on it too long. Same with the emitter leg in the middle. That's going to be the hardest to solder because the heat will flow through to the tab very quickly. So this is going to take a little bit longer to solder, but nevertheless it can still be done. And then just away, then straight off with the heat. Don't stay on them forever in a day. Again, onto the solder pad, warm that up, get solder flowing under the pin, then move to the top of the pin and solder that in place. So that's all done then. You see, is that now ready to go with the measurements. So everything's nice and tidy, cleaned up, all the flux residue and everything there. We'll just give these a little wash, these pins here, now with a cotton swab, and then we should be okay then. We should be good to go to then start doing the alignments. So once we've given these a little wash, then we're okay to progress on to the next stage of doing the alignments. Now what I suggest is, when we do the alignments, is use a low current power supply or a power supply with a current limit, and set the current limit to no more than about 4 amps. And the reason for that is because if these pots have turned out of spec and they apply too much current through or bias the transistors on fully, particularly these two, you could get shorted output or near short, and we don't want that because it'll cause a lot of problems. It might cause a fault condition further on in the power supply circuit to this. So we don't want any smokes, fizz bangs, anything like that, transistors sinking massive amounts of current because they're being biased fully on. So what we'll do is we'll just use a low current power supply initially, and we'll follow the alignment procedure now in order to align this board back as it should be. So back soon. Okay, so according to the manual, which I've now got open on the thing here, is we've got some measurement points which are, as we can see there, an inductor which we open, and as you can see there by that inductor there, W29 I think it is, and so W29 here, which is down on the board just here, we break that, the solder connection, so we can connect our multimeter there. And then further down, near the PA transistors, just in this area here, there's a pot resistor, a cement resistor rather, and the lead that comes off and solders to the PCB, we have to lift it up and then put an ammeter in there, because that's for the final amplifier transistors, is that. So where we are on the board when we're looking at this is the first inductor for measuring the idling current for the driver and the pre-driver is this inductor here, and we basically break the connection between the two and run it to the multimeter for the current measurement. So we can set this potentiometer, and then the second measurement, which is more difficult to see on camera here, is this cement resistor here, and we lift this leg up on this side because the power comes through and then supplies the current to these two transistors. So then we can set this potentiometer then obviously for that. So that's where we're at now. So I just need to break the connection first of all onto these two, and hopefully we can do that without too much trouble, and at least we've got that capability. I'll just get my little magnifier, because as I say, I'm about 2 feet away from the radio, so just get that there, and just flow it nicely if it starts to flow. That's it. So we can do the current measurement now for that. Another thing we just want to check briefly before we proceed any further now is we want to connect an ohmmeter, which we've got obviously on the meter down there. Set that up for reading ohms. We want to check the resistance between the tab of this transistor, or the emitter leg, and just check that it's not a direct short when it comes to reading ohms. And as we can see there, there's certainly a few ohms resistance there between the emitter and ground connection, which is a chassis of a radio. Had we had a 0 ohm short, you know, basically that reading that sort of level there, that measurement, then we would have a problem. It would mean that mica washer would have packed in, or the insulating collar on the insulating washer on the bolt may have failed. So that's always a good measurement to do, just to double check. We've got about 7 ohms there, which is good. So that proves that the insulating washer's working. Sometimes you can get little solder globules and things, microglobules, that get onto the mica washer, and when you tighten the transistor down, it penetrates through the washer and then bridges a connection that it should be insulating. Likewise, if you've not screwed the screw in properly and it's off center, the insulating collar may not be within the hole of the tab on the transistor, and it might be above it, and you think it's actually slipped into place into the tab in the transistor, because it's like it forms like a sleeve round the pin as the bolt rather goes in to the sleeve itself has a transistor tab here, and obviously the bolt goes in the top, right? So sometimes if the holes are misaligned and the sleeve sits on top of the transistor and it's not within the tab of the transistor, what happens is when you put the bolt through, the bolt touches the transistor tab, and then you think, right, because you're not paid attention while you're assembling it for whatever reason, maybe rushing, or you've just not seen, and then the transistor is effectively skewed, and then you apply power and then bang, because obviously the transistor tab short into chassis. But it is quite common sometimes for the mica washers to get contamination on them, particularly when you remove them and put them back in, unless you've cleaned them through like I do, and you can get sharp either metal filings or solder debris gets onto the flat surface of the mica washer, sticks to it, and then when it's compressed it penetrates through the mica washer then and shorts it out. So just be aware of that, but at least we've proved with that measurement that that's not the case, and we're ready to do the current measurement. Okay, we're ready to do our current measurements now. So just to explain, we've got 2 meters on the go. We've got this one here, which is an old style analog meter, which I've dug out. This is a high current DC ammeter, it measures up to 50 amps. Full scale, and it has 2 terminals on the top, so you can have a 50 amp scale or a 10 amp scale. The 50 amp scale is on the top and the 10 amp scale is on the bottom, just above the mirror. So the interest in this is because this is in series with the main power supply to the transceiver, This needs to be capable of measuring high current for when we're transmitting on the radio at full power later. But initially I've got it on the 10 amp scale, and the reason why we're using this meter is because the DVM behind can't measure more than 10 amps. So that's why we've got this in line, and I'm particularly interested to know what the quiescent current is, the current draw of a transceiver, and it's just in standby when it's powered up in receive mode. And we'll just need to check that against the service manual to make sure that that falls in spec and there isn't another potential fault somewhere. And then the other meter at the back here, which you can see, the digital voltmeter there, that's in current mode on a 10 amp scale again, and then the probes from that link to the power amplifier circuit. And the schematic diagrams and the procedural diagram in the service manual say you've got to unsolder W29, which is a wired link, which is these two black posts that are stood up. They're normally connected together at the top, soldered together, the wire. You have to unsolder those to break the connection, and then basically connect your ammeter in series, hence the reason why we've got these probes here on the 10 amp scale on the meter behind. So the idea with this measurement, according to the first step, is we put the transceiver into CW mode on 14.1 megahertz, and then what we do then is we adjust a potentiometer in the PA board using our trimming tool, which will then calibrate the current draw, the quiescent current, the bias current for the power amplifier drivers to 250 milliamps DC. So that's what we're going to do. Then we advance on to another test after it, which is where we unsolder. There's a cement resistor down here in the power amplifier, this cement resistor there. We unsolder one leg on that and then connect the ammeter again in series, and we're measuring that in that case for 500 milliamps, and we adjust R18, which is this blue potentiometer here. So the initial potentiometer we adjust for the drivers is this one here, that's hidden behind this relay, and then afterwards for the PAs then we adjust this potentiometer. So first of all, we'll just have a look at the quiescent current draw. So if I switch the power on and it's booting up, when I have a look here on the meter, it's within spec already. I can see should draw about 3.5 amps thereabouts, according to the specification in the service manual. And as we can clearly see there, it's spot on. Can't see a problem with that at all on the 10 amp scale. So there's nothing wrong there. That's as good. It says in the manual to set the transceiver to 14.1 megahertz, which it is, and the mode CW, the RF power, which is set here to be at maximum. I've turned the mic gain to minimum, so it's not going to pick any audio up from the mic when we key it up, and then we're good to go. So all we've got to do now is just do a measurement. So if I go to here with the zoom on the camera, and if I just turn that radio off a second. Right, so if we go to key the microphone up, incidentally I've got a power meter connected in on the rear on the RF socket number 1. So should this radio fire into transmit at maximum output power, it's not going to go into an open RF load and then create IVSWR and issues. So we've got the output of the connector there connected up to the Rhode Schwarz radio test set, which is more than capable of taking 150 watts. So yeah, so we've got that terminated. Right, so what we're looking for now on the current meter there, according to is 250 milliamps current draw. So if I just go onto that potentiometer, it's a bit high, so we'll just need to adjust it, and just need to get on it. It's a bit of a awkward devil to get onto. It's like got a weird crosshead on it. It's really weird. And of course I stuck it right next to the let me feel it. Sometimes you have to feel things in order to get the head to go on the potentiometer. There we are. We're on it now. Awkward devil. Right. So let's just give it a wipe. That wiper, and then we'll just gradually adjust it now for 250 milliamps. It's very sensitive. I literally got to just a gnats either way, and you know, just the amount of even just putting pressure on the trimming tools altering its measurement. It's a tiny little incremental measurement is this. Right, just a bit more. Now it's too much, we just need to get it down. Now it's too little. Oh, it's just so sensitive is this. It's unbelievable. Literally just touching the potentiometer is causing it to let's just crank it down a bit. There we are, look. Oh no. Now it's too low. Damn it. Well, we'll get there. Patience is a virtue. Oh, we're nearly there. Oh, there we are, look. 249 milliamps. That'll do me. Near enough is good enough. Right, so now then what we need to do now is power it off, remove the pros, resolder that link back together that's down here, and then Bob's your uncle. We can move on to the next phase of the measurement now, and easy wheezy, back soon. Okay, now for this measurement, we've lifted the resistor down there, we've soldered a wire in and connecting that back now to the meter as per the manual, and it says we need to adjust this potentiometer here for 500 milliamps, which we're going to do now, and we're just going to tweak that now for 500 milliamps hopefully. Oops, a bit too much current. Just get it down. Right, so that's news, damn it. That's a lot easier to adjust than the other one. Just settling it. There we are, look. Get that, just squeeze a bit more. There we are, look, 502 milliamps, 503. It'll come down, so I'm happy with that. It's yeah, I'll just give it a tweak again. It just needs to settle a bit, doesn't it? There we are, 499. I'm happy with that. Seems good enough to me. So that's that adjustment done. So I think we're okay. Don't think there's many other measurements other than that really. I think idling current adjustment for drives, idling point for finals. That's it. It talks about TX peak. Display frequency 14.1 USB. And then it talks about filter 2.4 kHz, supply audio signals to mic, transmitting. Right, so we should now be able to resolder that resistor back, and then we should be good to go then to do some actual transmitter measurements, and then let's see what it does. Let's see what we can get out of it power wise. Okay, so the moment of truth's arrived. After all that alignment and repair work that we've done, does the radio transmit at any high degree of RF power? So what we're going to do, we're just going to turn that RF power pot right down to minimum. So we'll start at minimum and work us way up. That way if there's any problems, then we're not going to cause any problems. And we've also got the ammeter here on the 50 amp terminal now. So we're now reading 50 amps maximum current consumption there. So let's see what the transceiver takes when it's operating at full RF output power. And then in terms of measuring the RF output power, we're using the Rhode Schwarz radio test set here. And so let's have a look now at the power. So we're on 1.9 megahertz thereabouts. I'm just going to transmit now. So we're getting some RF power there, 1.5 watts on FM, because I've got the transceiver set to FM so we can see the carrier wave power. And then I'm just going to start to increase the RF power now, gradually right the way up. I'm keeping my eye on the other meter as well at the moment for current consumption. Let's see if it does over 100 watts. So yes, 106 watts there in total power, 106 watts. 1, 2, 3, 4, 5. This is a test 1, 2. Yeah, so we're getting some power through there. We'll just try it on another frequency. This is 7 megahertz, and key up on that as well. So we're getting 100 watts there as well, so that's okay. Let's try this frequency, 3.7 megahertz, and then we're getting 107 watts there as well. So that's pretty good. I'm happy. So let's have a look at the current consumption then of the power meter. So on full power, we're transmitting, you're looking there on 3.7 megahertz anyway. That's about 20 amps easy, 20 amps. So that's something. And on 1.8 megahertz, still 20 amps. On 7 megahertz, 20 amps. On 10 megahertz, slightly less. 14.1 megahertz, about 18 amps. 18 megahertz, about 21 megahertz. So different frequencies. We're on 25 megahertz now. It's still doing 100 watts, but it's above the output power. Sometimes it's a little bit below in current. Now we're on 50 megahertz, and it's doing 97.8 watts on there. So yeah, it's really good, really good. I'm very surprised at it, to be honest with you. I'm very happy with that indeed. Yeah, so just been all the way through all the frequencies and what have you, but yeah, I mean, pretty good. I'm very happy with that. Can't grumble at all. I mean, the RF power on the Rhode Schwarz is very good. So let's just have another look. So key up again. So 107 watts. This is a radio test, 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. So we could do an SSB test as well. We could check that output power as well, but I think it'll be okay, but might do that next. So yeah, all in all, I'm quite pleased with that. We'll do some other tests and things now and see where we get to. Okay, so if you've done the alignments on the radio and you're still finding the transmit power isn't quite up to 100 watts on all frequencies, there is a separate adjustment which I'm going to show you, which you can do in order to try and mitigate that, and this is detailed in the service manual. But there are two potentiometers, one that adjusts the HF power for the HF band, and the other pot does the 6 meter 50 megahertz band, and then the third pot does the AM mod for all bands. So the two I'm going to show you is for that, but there's also some other potentiometers for automatic power control, or APC, and again, there are detailed instructions in the manual. But basically, in the bottom here, there are 3 potentiometers. I'll just zoom in on those and just see whether we can get to them. We'll just zoom in there, and then basically it's these 3 potentiometers just here. So this first one here adjusts the HF TX power, This second one adjusts the 50 MHz or the 6 meter ammeter band transmitter power, and this last one adjusts the AM. So it's just these two you really need to be looking at. So for example, if you've got it on say 21 MHz and the TX power say 60-70 watts instead of 100, you can adjust this potentiometer here to get that. It may mean it'll do more power on the lower frequencies, of course, but you can balance it out using these adjustments. So that's it basically. That's just a little rundown on that. So we'll just put it all back together and power it up and see how it works. Okay, we'll turn this down a second. Okay, so off camera I've spoken with 3 stations in the last 5 minutes or so. Chap in Spain, Christian, Alpha Oscar 75 Papa Alpha, and then another station in Slovenia that was Sierra 51 Delta X-ray, and then I also had a conversation with a chap in Belgium, Oscar November 4 Lima something November. Anyway, we had good contacts, all doing DX work, etc. But I don't put my call sign on the YouTube videos because otherwise I'll get 1,000 people queuing at my door with repairs to be done. So, you know, I keep anonymous as far as that's concerned. I hope you understand. But we prove the radio works. I've had the contacts with these stations. So with that, I think this is the end of the video, and I think it's only sensible at this stage to conclude due to the time. And thank you very much for watching, and hope that you've enjoyed the video as much as I have. And please subscribe to the channel if you haven't already done so. There'll be more repair videos coming along like this, and we'll see you in the next one. So thanks again. Bye for now.